One.
Ready? Hi. More summertime physics. This one is again all about Bernoulli. The principle that he came up with is, hey, when fluids are in motion, they exert less pressure than when fluids don't move. Okay? So fluids that are in motion exert less pressure than still fluids. So let's pretend that's you. And you are standing in a giant bank machine, but what that refers to is the atmosphere, the ATM. So you got a giant bank machine all around you. It's made of air molecules, and so there's air right there, and there's also air right there. And what you know about the motion of air molecules is completely random. So some of them are banging into you this way, and some of them are banging into you that way. And if nothing's moving, everything's fine, there's nothing, then you know that the number of air molecules banging into you on this side is pretty much the same as the number of the air molecules banging into you on that side. And if that's the case, there's no difference in pressure on either side. You feel normal. But now what I'm going to do is make one of those fluids move. And so what if I put a fan on the ground, and that fan is going to blow straight up, Paula Abdul. And so it's going to make these air molecules move that way. And now the motion of the air is no longer random. That means air molecules are moving up, fewer of them are banging into you on this side. So since fewer collisions this way, that means the air on this side will force you to move that way, to the right. And so again, because this motion isn't random anymore, there's no longer equal numbers of molecules on either side of you banging into you. These guys are too busy going that way. These will end up pushing you towards the moving fluid. So this moving fluid exerts less pressure than a fluid that doesn't move, and so you literally get pushed towards the fluid that's in motion. Okay? Now that's how it would work if you're standing and it's working on an axis, meaning it's pushing you right, left. Same thing applies for something that's pushing you up or down. And what I'd like you to envision now is, and it'll be awkward to draw, but what if there's some sort of a sword, if you will, lying flat, and that sword is moving horizontally into the wall here, and it's just going to slice a hole into the wall. But what if that wall isn't made of anything solid? What if that wall is made up of whipped cream? So now all these dots are whipped cream molecules. And as that sword slices through the whipped cream molecules, the sword might look like that as it goes through them. What that's going to cause those whipped cream molecules to do is literally split. So this whipped cream molecule has no choice but to move up. This whipped cream molecule has no choice but to move down. And as that sword moves, those molecules move up. And since that sword created a vacuum behind it, when those whipped cream molecules get to the end, they're going to slam back into each other. So they just move down and back up, and this one moves up and back down. And again, the whipped cream isn't moving, the sword is, and it's forcing that fluid out of the way at whatever velocity the sword is moving. Since it's a nice, even, uniform shape, symmetrical, top and bottom, then the distance that this whipped cream molecule moves is the same as the distance that whipped cream molecule moves. and it happens in the same amount of time because it matters about the velocity of the sword, and it's just one sword moving through it. And so they both move the same distance in the same time. They're both moving the same velocity, so they're both exerting the same amount of pressure because they're both moving. And since they're both moving, they're both exerting the same pressure. They're moving at the same speeds. There's no difference in pressure above or below it. And that's, again, true for something that's nice and symmetrically shaped. Same thing would be true if this were, say, a giant wedge flying through air molecules. Then that giant wedge would force this air to move around it, and since it pushed the air around, it would slam back into it down there. Same thing going on with that. But what if we could change the shape of the wedge or of the sword, and even though we won't change the speed of the sword, what we can do is change the speed of the air molecules flowing around it. And the way they'll do that is they will not make it nice and symmetrical. They'll make it the way you're used to seeing airplane wings looking, and that's something like that, where the curve of the top part of the wing is referred to as the camber. And if it's a very, very large camber, then the distance that that air molecule has to travel over here as it gets pushed up and goes back down is much farther than the distance the air molecule here as it gets pushed down and travels along the bottom of the wing, and then they reunite back there. So you can see this molecule has much farther to travel than this one does, as that wing is moving at a constant velocity through the air. Since this has a larger distance, and this has a shorter distance, but in the same amount of time, because the velocity of the plane is moving constantly, then this thing has no choice but to move faster than that. And if it's moving faster, then it's exerting less pressure downwards. And that's a very simplified version. I mean, there's a lot more complicated stuff going on, but literally, this molecule is moving faster than this one as the airplane slices through that fluid, and it has to cover much more distance in the same amount of time. So that means, since this is moving faster, and this is slower, then this is less pressure above, more pressure below, and that means the air below it will force this object, which we usually call an airplane wing, upwards. And since it's pushing it upwards, it's lifting the airplane, and that's where the term lift comes from. You can flip it over and put it on the back of a car, and now it pushes it downward. It's like a spoiler on a car that will increase the downforce to give you better handling, that sort of thing. But literally, it's pushing it upwards because it's a slower moving fluid, so there's more pressure. That force of lift then is equal to the change in pressure above it or below it. And so what that would be is the pressure, again, is then force divided by area. If we take pressure and multiply it by area, since pressure is force divided by area, force of lift then is going to be pressure times area. And so what I'll do is I'll say, hey, the pressure below times the area below, that's the below minus above, yeah, minus pressure above times area above. That difference is the force of lift, where this pressure times area is the force below it lifting upwards, minus the force, the pressure times area, pushing it down. If it's in level flight, then the force of lift is equal to the force of gravity, the force of weight of the airplane. And that just means this pressure times area minus pressure times is equal to the mg of the airplane. Okay? Now again, there's a lot more complex stuff going on, but for this level of a physics class, that's plenty conceptual enough to say, hey, just the difference in pressures due to the separation of the fluid that it's traveling through. All right? So there's that one. There's a bunch of other applications of this Bernoulli guy. And that would be a very common one is the speed of water flowing out of a pipe, something like that. So if we have a giant water reservoir, something about yay, and there's a pipe there, and maybe this thing is a water tower, so it's on stilts somewhere, whatever, and so water is coming out leaking like that. This is a very common application. Usually they'll ask you, how fast is that water traveling outside of that spigot? To do this, you'll set up the Bernoulli equation, which we went over on a different lesson here, but the Bernoulli equation is that conservation of energy applied to fluids, where you have the work is force times distance, the potential is mgh, and the kinetic is 1/2 mv squared. But just apply that to fluids, and instead of force times distance, we'll have a pressure at any one location plus the potential energy, if you will, at any one location, which instead of mgh, we'll use a rho g, and usually a y instead of a height, a y at any one location, plus the 1/2 rho times the velocity squared at any one location. So again, those three things together added up will always be the same as those same three things together added up at any two locations. So rho gy2 plus 1/2 rho v2 squared. Okay? That form is the Bernoulli equation. It looks pretty scary at first, but a lot of stuff is going to simplify down. So at this location would be the surface. Right now, I'd like you to visualize what is the pressure that this water molecule is feeling on the surface. And for that, again, visualize you're inside a giant bank machine. There's atmospheric pressure pushing down on that surface. So the pressure at the surface, atmosphere. Okay? The Y1 at this surface is whatever you care to call it. Call it whatever you want, it doesn't matter. And what I'd also like you to envision is this velocity at the surface, meaning how fast is this surface decreasing, moving downwards. And for all intents and purposes, since this surface area is so darn big compared to that this stuff's going nuts. But if you were to watch this, it would essentially be moving at 0 meters per second downwards. I mean, you'd have to come back a while later to notice any difference. Like picture a giant swimming pool draining or something. You know, looking at it, you can't even tell it's moving unless you come back an hour later and maybe it dropped a bit. So this velocity that it's moving down here, for all intents and purposes, we can call 0. Absolutely nothing. Down here, the pressure that's at location 2 now. What I'd like you to realize is we're not referencing the water pressure pushing it out. We're referencing what pressure this water molecule feels the instant it leaves that pipe. And what that water molecule is feeling is the exact same amount of pressure that that water molecule is feeling. There's an atmosphere here trying to push that water molecule back in. So that atmosphere is the same pressure that it's feeling up there, so the P2 is the same as it is up there. The Y location, you can be nice to yourself and say, well gosh, even though the ground level is down there, this Y we can call 0, and then that Y is just however much higher up it is above from that, it doesn't matter. And then the V2 is usually what they'll ask you, how fast is that going? Or sometimes they'll set up a problem and tell you how high this is off the ground and how far away it lands, in which case you'd use those 5 kinematic equations to say, hey, it went this far in that amount of time, whatever. Something along those lines. But setting these up, realizing that this isn't really moving at all at any one given instant, and realizing the pressure on both sides then is pretty much the same. When you plug these in here, you can realize that the pressures die because they're the same on both sides of the equation. Since Y2 I called 0, that pretty much dies. And the velocity of this surface we called 0, that one pretty much dies. So literally, the speed of that water as it flies out of that is due to nothing more than the additional pressure caused by the height of the water above it. And again, another interesting thing to realize is it doesn't matter how big this item is from an area standpoint. It could be a giant vat, or it could be something fairly skinny. The only difference is the skinnier this is, we would have to include a term for that velocity. But the height is what gives it that pressure to push the water out. That's really all it is. Okay, that's about it for that one. Another one we'll also see is, if you can kind of envision this, but in a different perspective. Just flip it where we'll know stuff from the bottom. Let's pretend this is the incoming plumbing in your house. So that's the incoming water, so this could be your house, and that pipe then goes boom up, and there's a little shower head. Okay, so you guys all know, you've heard the term water pressure. That's what we're going to be dealing with, fluids that are in motion. Let's pretend in our headsies that the velocity of this stuff is 1/2 of a meter per second. And again, let's say the area, or the diameter I should say, call it, I don't know, 2 centimeters diameter. And that's really all you need. Up here, let's pretend in our headsies that this guy 5 meters above that pipe. This diameter, it's going to get a little skinnier. Maybe it's 1.1 centimeter diameter. And so then there's 2 things we can ask you. Or if I say, hey, how fast does the water squirt out of your shower head? What you would do is literally plug it straight back into this Bernoulli equation. Oh, I didn't tell you the pressure at the bottom. Let's say the water pressure down here is, I don't know, 3E5 pascals. Okay, so this is the basement, or the incoming basement. So we'll have pressure in the basement, the rho gy in the basement, the 1/2 V squared in the basement. And set that equal to the pressure upstairs in the bathroom equal plus, or then you add that to the rho gy upstairs and the 1/2 v upstairs squared. Okay? If you plug stuff in there, there's two things you don't know. You don't know the pressure up there, and you don't know the velocity up there. So what we'll have to do is, since there's two things we don't know, we have to use additional equation, and that other equation is the flow equation we went over just a little bit ago, which means it's the area in the basement times velocity in the basement is going to be exactly the same thing as the area in the upstairs in the shower times the velocity in the upstairs in the shower. So we'll divide this by the area of the upstairs. We'll get the velocity upstairs. Once that number is in place, we can put it right there and then solve for the pressure that you feel when you're taking a shower. So the area in the basement, again, if it's 2 centimeters, that's the diameter. The radius is just 1, so it's again a pi r squared. So this would just be a pi times 1 centimeter squared. The velocity in the basement is 0.5 meters per second, and I know that's different from that, but it'll divide out because we're going to divide it by the area upstairs, where this pi is going to die, and this will be times 1.1, or half of 1.1, which I guess I should have been friendlier. Why don't we call it 1.0? And then it's 0.5 centimeters squared, and those die. And then another interesting thing to note is, hey, if that's 1 and this is a half, then the ratio of this being sliced in half, but it is squared. I know I crossed them out, but since it is squared, it's going to end up being 4 times this, which means the velocity upstairs is 1 divided by a half, or 1 divided by 0.5, but we end up squaring that quantity. It's 2, so it ends up being 2 meters per second. All right? So once we know that velocity, 2 meters per second, we can take the y, that is 5 meters. You know what planet you're on. You know the density of water is 1,000. Pressure upstairs is your goal. The pressure in the basement still given. The velocity in the basement is still given. Do the math, throw the numbers in there, and I think it was dancing around 2.5. It only drops a little, so the pressure upstairs is dancing around 2.5 E5 pascals. Okay, so the overall thing when you're dealing with fluids that are moving, things about, pipes or water shooting out of whatever reservoir, set up the Bernoulli equation. If there's more than one thing you don't know, then chances are you'll have to use the flow rate equation to put something that you don't know to substitute it in, to keep going with whatever it is. But it's the same thing, same concept. The conservation of energy is how you use the Bernoulli's principle. In fact, the principle is just a very specific example of a very broad application, like a law. That's all the principle is a very specific application of a law, and that's it. Cool. So hey, Bernoulli, yay physics.